Optimization. Often in businesses and real-world situations, there is a need to maximize profit, minimize cost, minimize travel time, etc. We call these optimization problems. Now that we have a deeper understanding of calculus, we can apply it to these types of problems using given constraints. The best way to learn these types of problems is by practicing. And we'll begin by going over some helpful steps. First step, assign variables to unknown quantities. Drawing pictures is helpful. Step number 2, define the constraints for your variable if there are any. Step number 3, decide on the equation that needs to be maximized or minimized. And then write the equation in terms of only one variable. Step number 4, take the derivative of the equation from step number 3 and set it equal to 0 in order to calculate the maximum or minimum value. Because remember, when a derivative is set equal to 0, it will find the points where we have a horizontal tangent line, or where that derivative, or the slope of the tangent line, is 0. And then step number 5, check your answer against the constraints to make sure that it is feasible and makes sense. And step number 6, answer the question fully. And it's important to note, make sure to test endpoints if the interval is closed. Here's an example. A farmer is creating a rectangular pen for animals and has 160 feet of fence. The side of a barn will be used for one side of the fence. What length and width would produce the largest area for the pen? And what would the area be? Let's get started. Begin by drawing a picture. We know it's a rectangle, and we have a barn as one of the sides. So we have a width coming out, a length that is parallel to the barn, and another width. And then since we can't use more than 160 feet of perimeter, or fencing that represents the perimeter, that's our constraint. So we can set up an equation using the perimeter. So we have 160 is equal to 1L plus 2W. And then if we solve this for L, by moving 2W to the other side, we get that the length, or L, is equal to 160 minus 2W. We also know that the area of a rectangle is equal to the length times the width. So that's the other equation that we're going to be using here. Since we've already solved the perimeter equation for the length, we can substitute 160 minus 2W in for the length in the area formula. So we would have that the area is equal to 160 minus 2W, all multiplied by W. And then if we distribute the W through, we get that the area is equal to 160W minus 2W squared. And then we can find its derivative using the power rule 2 times. So the derivative of 160W is going to be 160, and the derivative of negative 2W squared will be minus 4W, or negative 4W. So here's what our derivative of the area formula is. And the next step in solving this problem is to set our derivative, which was 160 minus 4W, equal to 0, and then solve for W. So we can add 4W to this side, and we will get that 4W is equal to 160, and then W will be equal to 40. So we found our critical value for the width being 40 feet. Now, what will this critical value produce? Will it produce a maximum or a minimum? Well, we can find that out by calculating the second derivative. So A prime was equal to 160 minus 4W. Remember, we set that derivative equal to 0 to solve for W. So if we take the derivative of our first derivative, we'll get the second derivative, A double prime. And A double prime will equal negative 4. And A double prime being negative 4 is less than 0, meaning that we have concave down at that W equals 40 value. So because it's concave down, this will yield a maximum value. And now that we know that the width is 40, we can substitute it into the length equation and solve for the length. So 160 minus 2 times 40 is 160 minus 80, which is 80 feet. So the length is 80 feet and the width is 40 feet. So it asks what length and width would it produce? Okay, we answered this question, but what would the area be? We still have to calculate that by multiplying our width and length together. And when we do that, we will get that the area is equal to 3,200 square feet.